Yes, I can see it. Hopefully everyone else can.
Okay, you can see the slide well, right?
Yeah. Yeah.
Okay, so um, perhaps to begin my talk, I need to explain what my talk is going to be about. The title is a bit unclear on purpose. I wanted to create some small intrigue. Let me start by explaining the main idea of the talk. I will start with something which everyone in the audience knows well. This is the eigenstate normalization hypothesis, which I will understand quite narrowly as the ansatz for matrix elements in some many-body quantum system. Throughout the talk, for simplicity, you can keep in mind some your favorite version of spin chain, preferably non-integrable spin chain. Now, as an ansatz, it applies to chaotic systems and also to some interacting integrable systems as well. It only the only non-trivial information ETH ansatz includes is the statement that matrix elements can be described statistically, that we don't care about individual values of matrix elements, but we only care about their statistical properties. And in particular, those are encoded in this function f, which I will call the power spectrum. Okay. Now, the original ETH ansatz or formulation, original formulation of ETH postulates that matrix elements, well, the coefficients which enter matrix elements ansatz, those coefficients are independent. They're random independent variables. Of course, that cannot be true because we start with any given quantum system and any given observable A. Nothing is random, everything is fixed. You can do direct diagonalization and calculate your matrix elements. To even simplify this thought, think about a spin chain and take, as an observable, take a Pauli matrix. And the Pauli matrix would satisfy a simple identity. Pauli matrix squared is equal to 1. That's an algebraic identity. And for this identity to be satisfied, coefficients Rij certainly have to be correlated. So of course, we cannot take matrix elements to be uncorrelated. But in many contexts, it is enough to say that Rij uncorrelated. For example, if you try to calculate the two-point function and you plug the ansatz into the expression for the two-point function, only variance of Rij matters. By definition, Rij have unit variance, and we of course know very well that only function f will be in the answer. So another example when correlations of Rij are important was given a little bit more than 3 years ago in a paper by Foini and Kurchan, and then later developed by an Oxford group, where people started noticing that if you want to describe correct behavior of four-point function, you also need to consider correlations of matrix elements. Okay, and approximately around the same time, a little bit more than 3 years ago, I also wrote a paper where I was pointing out that, in fact, correlations of matrix elements are important even if you try to describe thermalization dynamics. So this statement may be not a conventional one, because when people describe thermalization, the first thing they think about is a two-point function. And as I just said, two-point function is independent of correlations. But I will explain in the rest of my talk that there are other probes of thermalization. And if you want to describe thermalization accurately, even at leading order, if you wish, there are no corrections, just leading order behavior, dynamics toward equilibrium, correlations are very, very important. So in this talk, I will be describing, I will not be able to describe correlations. I will explain why correlations are important. And I will also ask the question, is there any scale beyond which correlations are again unimportant? And this particular scale, I will call the scale of quantum chaos. And as a part of this talk, I will also describe when the scale, I will describe the value of the scale if you wish. So this is just an introduction and motivation. So let me give you a small review of different timescales relevant for quantum dynamics. One of these timescales is the Thouless time or Thouless energy, which marks the onset of random matrix behavior at the level of energy spectrum. If you have a theoretic quantum system, and if you look at energy levels which are sufficiently close to each other, then you will see level repulsion. And in fact, you can consider other statistical properties of energy spectrum and see that when energy difference is sufficiently small, all of them are described by random matrix theory. This is the Behiga's conjecture. And the scale, the energy scale or the time scale, which marks the onset of this behavior is called the Thouless time. There is another scale, which is also very important, thermalization time. You consider a two-point function, and with time, it approaches a plateau value. This plateau value, I wrote a constant, but actually we know what it is equal to. It's roughly 1 over volume. It scales like 1 over volume. And the saturation happens around the time which we call thermalization scale, or at least I will call in this talk thermalization scale. Instead of thinking of two-point function, we can think about the power spectrum, and at the level of power spectrum, inverse scale 1 over tau would mark the region where this power spectrum is approximately constant, or people also speak about the plateau of the power spectrum. So this is well known and well understood. Now, those two scales, the Thouless time and thermalization time, are not distinct. We know that for the single particle case, they're the same. And more recently, there was additional evidence that they're the same even in the many-body case. I'm referring to recent works by the Oxford group and also Dymarsky and collaborators recently in the last December and even before that, we are discussing the thermalization timescale and arguing that it is the same as the Thouless scale. So I think there is no controversy, and throughout this talk, I will simply assume that the Thouless scale and thermalization scale are the same, at least when it comes to the scaling with the system size. Of course, you can define them slightly differently. There would be some relative coefficient, but when it comes to the scaling with the system size, they're the same. So now I want to introduce my own definition of onset of chaos. I will say that I will introduce the time scale capital T, and this is the time scale at which matrix elements of local observables don't have to be correlated anymore, that I can treat them as completely uncorrelated. So that time scale will mark the onset of random matrix behavior at the level of observables, not at the level of energy spectrum, but at the level of observables. And naively, you might think that this scale would simply be Thouless scale. It doesn't really matter whether you want to use random matrix theory to describe local observable or you want to describe energy spectrum. You think it would be the same energy scale, but I will argue that they're parametrically different. Namely, the time scale which marks the onset of random matrix behavior for the observables, it is parametrically longer than Thouless time. So this is one of the main results of this talk. Okay, so maybe I should reiterate what I have so far. I call the onset of time, I call the onset of chaos the scale at which correlations between matrix elements are not important anymore. And in the rest of the talk, I will be discussing what I can say about the scale. So before I go into this, let me quickly remind you the expected behavior of a two-point function in a one-dimensional spin chain or any other quantum system. We think that the autocorrelation function will approach a constant. Well, I write the subscript C, which means connected, and it simply means that I subtracted the asymptotic constant from the value of this two-point function. And after subtracting this constant value, this autocorrelation function will approach 0. as a polynomial of time, and the power is as a power of time, and the value of alpha tells me what kind of transport I have in the system. If alpha is equal 1/2, I have diffusive transport. If I have alpha equal 1, I have ballistic transport, and so on and so forth. But as I was already mentioning, this power law behavior will saturate around thermalization time, and after that, I will approximately have a constant value. But there is another much more sophisticated probe of chaos when I calculate expectation value of the same local operator in some highly excited out of equilibrium state. I take some state psi, which is out of equilibrium, and I calculate the expectation value. And if I wait long enough for all the transport modes except the slowest one to die out, I will have an exponent which is governed by the same thermalization timescale. So depending on your psi, so this is a completely universal statement. And by the way, to sort of check if those statements are correct or to connect them with something, with some other pieces of knowledge, you can think about classical diffusion on a circle, and then Green's function for the classical diffusion on a circle would be given by the theta function. And you can very simply clarify that my picture here is completely compatible with this exact result. So the statement that expectation value of a local operator will go exponentially, it's a completely universal result. But then for most psi's, for example, for psi's which describe local excitation, the coefficient in front of this exponent will be 1/volume suppressed. But there are, of course, states which describe macroscopic displacement of energy or microscopic displacement of some other quantity, of other conserved quantity. And if you have a macroscopic displacement of conserved quantity, then the coefficient in front of this exponent will be of order 1. And this is, of course, important for us because I will be considering these states in my consideration. Now, to further confirm that this picture is correct, and not only by comparison with the theta function, which is a Green's function of diffusion, I will give you some results of numerical computation. I considered a non-integrable Ising model numerically. I considered sufficiently long spin chain with 24 spins and open boundary conditions. And I consider highly excited psi, which describes the displacement of macroscopic amount of energy. And my operator A was this the Pauli metric sitting at the edge of the spin chain. And because of the Lieb-Robinson bound for a while, my operator didn't know that the equilibration is coming, and then the exponential decay started. And then also the numerical result for the 2-point function. So those two plots, they have exactly the same time axis on purpose because I wanted to show you that by the time when 2-point function pretty much became 0, I subtracted the constant value. The expectation value of a local operator in this special state, highly excited state, was still going down exponentially. So you can see very clearly that here I have essentially 0, and here I still have exponential behavior, excuse me. And just to reiterate this point, I replotted the same guys in a slightly different coordinates. The 2-point function was replotted in the log-log coordinates, such that the linear slope clearly shows that you have t to the power minus alpha, and alpha is equal to 1/2. And this guy, I replotted just the horizontal, excuse me, just the vertical axis was logarithmic. And in this case, this exponential behavior becomes a straight line, and the slope of this straight line is related to Thouless time. And you can see very clearly that the behavior predicted here continues for a while, and then it stops because the 2-point function saturates, and it saturates around maybe t equals 70. But around t equals 70, my exponential decay still continues. Okay, it still continues. So what I want to emphasize with these pictures is the following. If you somehow assume that at the Thouless time or at thermalization time, you don't need correlations of the matrix elements anymore, if you assume that, then you will have to assume that all this nice exponential behavior after Thouless time all this exponential behavior is somehow describable by non-correlated Rij. And I will try to give you a quantitative, rigorous argument that this is not possible. So before I actually do that, I've just tried to sort of reiterate the intuition. This nice exponential decay is due to correlations of matrix elements. I cannot, in full generality, rule out that this is impossible to have it with the uncorrelated Rij, but this is very unnatural. And now I will try to give you an argument which actually shows that the onset of uncorrelated Rij have to be parametrically longer than Thouless time. Okay, to build my quantitative constraint, I need to use the following trick. Some mathematical preliminary. Let's consider a rectangular function. A rectangular function is 0 for the argument outside of a narrow strip, and inside the strip, it is equal to 1. So here I have a function of omega. For omega larger than omega 0 or smaller than minus omega 0, it's 0, and inside this strip, it is equal to 1. And the Fourier of this rectangular function is given by the sine divided by t. Now, what will happen if I consider an expectation value of a local operator and multiply by this sine filter? If I do integration over time from minus infinity to plus infinity, I will essentially apply this rectangular filter to the energy domain. So I can rewrite the same thing in the following form. I first can use the transition from Schrödinger picture to Heisenberg picture when my operator is time dependent. And then I apply the filter in the energy domain. And basically can write down that this expectation value will be an expectation value of the original state, but the operator now is different. This is a different operator. And in the energy eigenbasis, this operator looks as follows. It is exactly the same operator as it was before inside the narrow strip. I cannot highlight it, but I will show, and hopefully you can see the mouse. So inside this narrow strip, this is exactly the same matrix elements as they used to be, but outside of the strip, I have 0. Of course, this operator still satisfies the ETH ansatz, but with a new power spectrum. The new power spectrum is equal to the old power spectrum inside the strip, and it is equal to 0 outside. Okay, why do I care about this filter and why it is convenient to have such an expectation value? It is convenient because I actually can universally bound this expectation value. This expectation value can be bounded from above from any state psi 0. It is a completely mathematically trivial statement that the expectation value of this operator is bounded by the largest eigenvalue of this operator. And it doesn't matter what my state is. I just need to bound this, the largest eigenstate of this operator. So I'm on purpose trying to show you 2 slides simultaneously because the next step would be the following. The next step would be to say that this delta E is sufficiently narrow, and I can now say that Rij, or matrix elements Aij inside the strip, are completely uncorrelated. If they're completely uncorrelated, this means I'm describing some band random matrix. And I can calculate maximal eigenvalue of a band random matrix analytically. And to calculate this eigenvalue, all I need to know is this F, because the variance of Rij are equal to 1, and we know that Rij are we assume that they're independently distributed random variables. So basically that's all. I now can bound the expectation value by just this function, assuming that my delta E is sufficiently small, or it means that my capital T is sufficiently large, such that matrix elements can be considered as uncorrelated. Okay, there is some subtlety here. There is some mathematical subtlety. I do not know if I have time for it, but let me just say the following. You can say, well, maybe we were playing the game that there is an energy scale, and beyond this energy scale, matrix elements are uncorrelated. But it only corresponds to matrix elements inside a very small square, which means that Aij and I prime, J prime are uncorrelated when both EI minus EIJ and EJ minus EJ, excuse me. Okay, what I was trying to say that maybe inside a small square, matrix elements were uncorrelated. Maybe that's the game we were playing, but there is a danger that matrix elements are still correlated between, let's say, left, right, left, upper left corner and bottom right corner. And certainly I don't want to go into mathematical details, but there is a way to mathematically bound a maximal eigenvalue of such a long band matrix, which may have partial correlations along the diagonal, but no short range correlations between matrix elements. And the price you pay is just, instead of this 8, you have a much larger coefficient, something like 36. So this is the only price to pay. So this is a subtlety which I will disregard for now. So now let's see what I have. If I apply this time filter, I can relate everything to this expectation value, and then I can bound this expectation value by this integral. And this integral, of course, can be related to the 2-point function of my original operator, because this function f is a power spectrum of it's a power spectrum of operator A. So if I put everything together, I have a bound on the scale delta E, beyond which I can assume that my matrix elements are uncorrelated. This is my bound. It works for any state psi, and it works, it becomes stronger if I try to maximize the left-hand side with respect to psi. So basically on the left-hand side here, I have the square of this expression. And I need the square of this expression because I'm aiming of bounding the left-hand side with the maximal eigenvalue square. And this expression is simply this expression written in terms of 2-point function. So, okay, so this is my bound. This is my bound. And it's completely universal and even analytic. So now I want to discuss how this bound behaves. This bound is a bound on energy scale delta E, but of course I care about time scale more. So I say that delta E is equal to 2 pi divided by T, and I try to calculate left-hand side and right-hand side. And I know that left-hand side is given by the exponent governed by the thermalization time. So the result of calculating left-hand side is equal to this. And the right-hand side is also governed by tau-less time, but this time there is a power law. So as a result, I have something like this. Okay? It's very clear to see that the power of capital T is different because capital T is an inverse to delta E. Here, delta E enters. If you take delta E to be very, very small, you can substitute sign by the argument. So T cancels as you simply have delta E. But this whole expression is squared. So on the left-hand side, you have delta E squared. On the right-hand side, you have simply delta E. And that is the difference because here you have capital T squared and here you have capital T. If you put everything together, you have the following bound. You have T larger than thermalization time multiplied by something. What is this something? If you calculate the something, this term carefully, it will be tau to the power alpha. But tau to the power alpha is exactly the value of a 2-point function when it saturates. And the value of the 2-point function when it saturates should scale with the volume as 1 over volume. And therefore, here I have the following bound. And obviously, the dimension is wrong. Dimension is wrong. This is because I'm missing some dimensionful coefficient. But what is correct is the scaling with the system size. My hypothetical scale capital T is parametrically larger than thermalization time, and it's actually larger than thermalization time multiplied by volume. So now I want to understand what it means. Now, strictly speaking, for my argument to work, for my argument to be valid, alpha has to be smaller or equal to 1. And for alpha to be smaller or equal to 1, this will only work if I have one-dimensional system. If I have multi-dimensional system, let's say 2 or 3-dimensional system, and I have diffusion, alpha will be too large, and then this quantity will be 1 minus alpha will be negative, and my argument will not work because to go from here to go from the integral here to here, I actually need this integral to be saturated at late times. And it will be saturated at late times only in one dimensions. So when I was saying volume, I formally did this calculation, but it's a rigorous calculation only in one dimensions. So in one dimensions, I have this formula. And for diffusion, tau time squares grows quadratically with system size. And for diffusive system, I have my time scale scaling as L cube. So this is my prediction. But I want to emphasize that even if you're completely agnostic, about the type of transport in your system, if your system is local, you always have Lieb-Robinson bound, and Lieb-Robinson bound tells you that thermalization time scales at least linearly with the system size. And therefore, even if you're completely agnostic about type of transport and scaling of tauless time or stuff like that, even in that case, I can guarantee that the onset of independent uncorrelated matrix elements cannot happen sooner than L squared, because tau can never be smaller than linear size of the system. So this is a constraint on matrix elements from locality, and let me maybe emphasize that. What I get here is a constraint that matrix elements of local operators must be correlated due to locality. This is a completely universal result. So now I was also trying to give some numerics, but this numerics should be taken with a small grain of salt because of this coefficient, which I can fix conservatively, but I think actually to see where the scale is, to identify the scale by marking the saturation of this inequality, the scale should not be taken conservatively. It should be taken to be at its actual value when everything is uncorrelated. So let me skip that. I only have maybe 2 or 3 minutes to speak. Let me skip that and try to, yes, I assume I started like 2 or 3 minutes late. That's why I said that. So let me try to interpret this result. I give the following interpretation of this result. I think that the correct scaling happens when I try to equate the expectation value of my local operator with the asymptotic amplitude of quantum fluctuations. This is my exponential decay, but my exponential decay sooner or later becomes erratic quantum oscillations. And the scale of erratic quantum oscillations is e to minus s, And if I try to calculate at which time scale this erratic quantum oscillations will start, then I will get the scale, thermalization scale multiplied by entropy. It has the correct dimension and entropy scales with the volume. So I propose a hypothesis that the correct onset of quantum chaos is actually the end of thermalization. And before thermalization ends, you really need matrix elements to be correlated. And of course, this time scale is parametrically larger than the tauless time. So I have some numerical evidence based on the recent work we did with Jonas and Robin and Johan, like around a year ago. We calculated the eigenstates of narrow band matrices, which I described above. We calculated it numerically. And depending on delta E, if delta E is very large, you have something complicated, but if delta E becomes small, you have a Wigner semicircle, which pretty much marks the transition to the independent random variables. And the work I will probably skip some philosophical discussion, what works, what doesn't work, but simply say that we numerically saw, so what I want to emphasize that we numerically saw that there is a time scale or there is an energy scale at which correlations between matrix elements disappear. We saw that. And we schematically saw that this scale is much larger than tauless time. But we are not there yet to numerically confirm that this scale actually goes as L cube. This is still work in progress. And this is my summary. I gave you an analytic argument that onset on chaos, which is defined as the scale at which matrix elements can be truly uncorrelated scales as tau multiplied by the system size in 1 dimensions. And I have a conjecture that the true scaling is tau-less time multiplied by the entropy. So that's all. Thank you.
Thank you very much. Are there any questions? I don't see anything in the chat. Yeah.
Sorry, can we just
Vedika?
unmute and ask? Yeah. What do you think happens for Floquet system? Because they're, based on these random matrix calculations, there's some expectation that the tau-less time is either order 1 or log L. And but the system still has localities. So what would you predict in your framework for that?
It's a great question, and I didn't think about it. I need to think if for Floquet systems we can meaningfully define off-diagonal matrix elements. What concerns me is the following. In my consideration, I was relying on the fact that there is a state psi, which is highly out of equilibrium, which will take very long time to equilibrate. And for any spin chain, I can explicitly construct such a state by taking equilibrium state, taking energy from half of the system and shuffling into the other part of the system. So that's, or in half of the system all spins down, and on other part of the system all spins are up. For Floquet, of course, I can have a state like that, but I'm afraid there is no conservation laws. So I don't know if that state will be truly long-lived or it will equilibrate right away. And I suspect the later, so it might be that my argument will not produce anything profound. But it's a good question. I need to think about it.
Okay.
Tolia, there are a few more questions. Let me abuse my my chair, being chair, and ask you a question. So your result is for a particular set of operators that actually have overlap with energy, so they diffuse. But for example, if I took the energy current operator that is odd, for example, or some odd operator that will have tau-less time or a decay time of the correlation function that's just order 1 and not order L. For this operator, you would just have the same scaling of it, just the scaling L, or
yes, I would be, yeah, I would not be able to do the calculation in my head, but if you say that there is no psi, if you have an operator which thermalizes very quickly in any state psi, then I think it would be a trivial calculation to do. And my expectation, also I need to do this calculation, would be that capital T will be simply equal to tau-less time. Mm-hmm. But to be careful, I actually need to do this calculation and maybe send you the result over email or something like that.
Might be important, for example, for current operator.
But you need to be careful to completely to make it orthogonal to energy or any other conserved quantity.
Yeah, by symmetry you can orthogonalize, for example.
Well, yes, in field theory, I'm also trying to think about extension of this argument to field theory, conformal field theory. And in conformal field theory, of course, operators are orthogonal, and therefore this argument would not work right away. Because most in conformal field theory, all operators decay rather quickly, except for some. So basically what you say works.
Okay, thanks. So now there are a few hands raised and there is a question in the chat. So let's start from the raised hands. Stematios first, can you unmute yourself and ask?
Can you hear me?
Yes.
Can you hear me?
Yes.
We hear you.
Yes. My question is the identification of the scaling with the time with the entropy as proportional to volume. Does that mean that there's some subtlety with the holographic interpretation? Because in a holographic interpretation, the entropy is assumed to scale as the area rather than the volume. So would that have something to do with any fast scrambling issues, for instance? That would make the entropy scale faster?
You're muted, Tolia. You're muted.
I somehow got muted. I was discussing states with finite energy density, and the matrix elements, those ij's, they would correspond to energies which are extensive. So the energy density is always finite. And even in holographic systems, if you have finite energy density, the entropy would be proportional to the volume. It's only the property of the ground state in certain systems that the entropy grows as area or as a logarithm or something like that. But all of I was saying it's for finite energy density.
We will have slow scrambling, besides.
Tolia, there is also a question in the chat of the same flavor. If there is a simple holographic interpretation, a question by Jan, I guess partially answered it.
How do I access the chat?
Oh, you can just.
No, yeah, I just read it. Does this new scale have a simple holographic interpretation?
That's something I need to think about. These are great questions. I don't know the answers though.
Okay.
Yes, we'll try to think afterwards, but yeah.
So there is another question, raised hand by Alex Bellin.
Yeah, hi Tolia. My question is also about holography, and I was trying to reconcile some of the things that I know in holography and how they relate to your talk. So if I understood correctly here, you're assuming that there's essentially an order one number of local degrees of freedom, and you're asking how things scale with the system size. Now, in holography, we're interested typically on putting, say, a CFT on the circle and considering a large number of local degrees of freedom. And there, I think the Thouless time and thermalization times do not agree, but are parametrically separated by n. So I'm trying to understand what would happen there and how that fits into your story.
This is a great question because right now I'm trying to extend this argument to two-dimensional CFTs and trying in part understand how central charge will enter. So indeed, in my talk, I equated thermalization time tau and Thouless time tau something. But if you have other large parameters like large central charge, they might not be the same. And again, I don't have a full answer yet, but hopefully soon. So let me just say that, and that's yes.
All right, thanks.
Are there any more questions for Tolia? Yeah. Okay. So it's exactly 10:41. I guess we can start